begin. Let's begin our influence line. This time it's going to be for the indeterminate structure. So as far as I'm concerned, I don't think anybody has fallen in love with the influence line that much. Okay, so let us begin by reviewing the most useful thing, and we are going to use the concept from that useful theory, that is Muller-Breslau. Okay, Breslau principle. Okay, now Professor Muller-Breslau simply state that if you allow the design function on your structure to go free, the deflected shape of your structure will be somewhat similar to the shape of the influence line. For example, if we have a simple beam like this, okay, and I am interested in the reaction at A of this beam, I will allow the reaction at A to go free. So I can allow the reaction at A to go free by adding a roller in this direction, right? So your beam is free to go under the reaction. So when that happens, your beam, because simply we have the determinate structure now, so if we remove one restraint, you know, it becomes somewhat unstable and the shape is straight like that. So your beam is going to go up like that, right, under the influence of the RA, if you don't restrain RA. So the that means the influence line of RA will be just the shape of this beam when you let go of RA. So the shape of the influence line is going to be that, exactly that shape. Okay. Oh, it's a straight, and you know, I have trouble grading sometimes because the way you write a straight line, sometimes your straight line and doesn't look straight, sometimes your curve too straight. You know, if I have any doubt from now on, I may not give you some necessary points. Okay, so the shape is similar. Now, once you figure it out, the shape, you can figure out the magnitude of your influence line as well by saying the influence line is constructed by putting the unit force on the structure. So if you're talking about the influence line of RA, the reaction at A here should be equal to 1, or the unit load itself, when the load is on top of A. So that becomes the shape of the influence line. Okay, so this is the, let's say this is the reaction. Okay, next, let's see the shear. Okay, let's say this is reaction. Next, let's see the shear. Okay, again, if I have the simple beam and I want to know the shear somewhere, you know, along the beam, so I'm just gonna allow the shear to move freely by adding a roller there. Okay, and the sign of positive shear, it's like this, right? Up on the left, down the right. So it's down on the left and up on the right. So when I allow this to go free, this downward shear will bring this down because it's on the right of the left portion, right? And then this one will bring this up. Okay, so that becomes the shape of the influence line of the shear. Let's call this maybe point B. Okay, so the shape becomes, it doesn't have to be in the middle, you know. So let's say the slope should be the same, and the value here This is where the shear changes, right? So when you have the unit load here, the magnitude of this is equal to 1 as well. All right. And let's say if you, I can give you more information. If this portion is A, that portion is B. This is going to be A over L, right? And this height is going to be B over L. But you can figure it out to maintain this, and the slope should be the same. Okay. Now is the moment. All right. If I want the influence line of the moment, say positive moment, I will allow the moment to go free by adding a hinge to the structure, okay? And say this is your positive sign convention for the moment, right? So to the left is this and to the right is that. So, you know, I don't want to write force here, it's messy, but that's fine. So for the left member, it's going this way. For the right member, it's going that way, okay? So that means with a hinge, with the help of a hinge, your structure can just fold up like that, right? So that becomes the shape of the influence line of the moment at B. Okay. And let's say if this hinge is anywhere, using the same AB, you know, this moment right here, the height is, if it is created by the unit load, so it's PAB over L, the moment is 1 multiplied by A multiplied by B divided by L. Okay, it's not 1. Okay, so that's basically how we can use the Professor Breslau to say obtain the shape of the influence line and use our structural knowledge to calculate for the numbers necessary. Okay. I can give you a further review by, let's look at some structure. Okay, let's say we have, okay, the beam looks like this. Let's say this is a hinge at B. This is a roller at C, and we are interested in point A as well. Give you some dimension. This is actually, we're not going to do something like this, you know, for the indeterminate structure, but just for the part of the review, let's do it. 1.5 meters and 1.5 meters. This is 6 meters. Okay, so whatever you want to know on the structure, you just allow it to go free. So let's say if you want to know RB, for example, influence line of RB, you just allow RB to go free, right? So your RB can go up. So therefore, RB can push the beam up, so your beam will move up like this. All right, and therefore that becomes the shape of the influence line of the RB. And in terms of the magnitude, we know that when you place your unit load at B, it is going to be equal to 1 at B here. So that must be 1. And therefore, it means that the height here, you need to use the similar triangle. So it becomes 3 over 6 or 1, I mean, not 3 over 6, 9 over 6, okay? Or 1.9. Oops, too small. Or 1.5, okay. So that's the influence line of RB. Okay, for let's say influence line of C, you will allow the C to go free this time. If C goes up and B is right there, so where B used to be, it has to be 0, right? And then C will go up. But because C goes up, this H will come down. That's where the line of 0 is. Okay, so that becomes the shape of the influence line of RC. Maybe that is too long. Let me erase that so that it looks okay, to be the same as the one on top. Okay, and now we know that the value of the reaction at C will be equal to 1 when we place the unit load there. So this is 1. So again, using similar triangle, you will come to the conclusion that this is minus 0.5 because it's 3/6, right? So that's RC. And let's say if I want to know the moment at C, moment at B, if I want to know moment at B, that means I will allow the MB to move freely. Okay, so it's like this. Okay, and you should notice that if you understand the behavior of the structure, you should know that if there is a load outside of B, B will have negative moment, right? But when the load comes inside between B and C, it becomes a simple beam because there's no load outside B and C. So it is a simple beam. So you shouldn't have moment at B because it becomes a simple beam. And if you apply the Muller-Breslau again, you will see that because of this moment, this part can come down like that, but for BC, it won't move. So for the moment at B, the shape of the influence line becomes just like that. Okay, just moment due to cantilever. And we have 3 meters, and you know that this value is going to be equal to the unit load multiplied by the arm of 3, so it's minus 3. So that's moment at B. So if I want to apply, if I want to know the, let's say, moment at A, this is my point A. If I want to know moment here, it's again, I add a hinge at A to let moment at A move freely. And on the left, it's like that. On the right, it's like that. On the right, it cannot move because we have 2 supports. On the left, if that is the moment, the member is free to come down like that. Okay, so that becomes the moment at A. I should, you know what? Okay, and then moment at A. Oops. Moment at A. It should begin here where A is, and then the rest is 0. And the value of moment at A shall be, you know, when you apply the unit load there at the tip of the structure here, multiplied by 1.5. So that becomes minus 1.5. That is your moment at A. Okay? You want to do the shear a little bit? Maybe. But the shear at the support is kind of difficult, and I don't think we're gonna do that again. So let me show you, let's say if it's a shear at A. So you allow the shear at A to go freely, right? Let's make a contrast by using red this time. The positive shear is like this, right? So on the left, it's down. On the right is up. Okay, this is on the left. on the left, on the right, on the right. So this one can come down a little bit, and you can force this to go up because you have two reactions. So that means the influence line of the shear at A will be just like this portion, and it is -1. Okay, so that's Muller-Breslau for us. Now, when it comes down to the indeterminate structure, what's going to happen? Okay, this is determinate, so you can just go ahead and do anything about it. But when it comes down to the indeterminate structure, I'm not going to do the truss anymore. Nobody's going to use that.
Yeah, can you go back a little bit?
Can I go back? Yes, I can. Am I going too quickly?
Thank you, teacher.
Pardon me?
Yeah, I finished yet. Thank you, teacher.
Okay. I asked if I was going too quickly, and you said thank you. Oh.
Oh no, teacher.
I think you know. First of all, this is the old stuff. Second of all, we are not going to do anything maybe extensively as this. We may do something about this, you know, but yeah, it's yeah, we've done it before. Okay. So let's say let's calm down a little bit, because I only plan to like introduce you a little bit back to the influence line. So this is the old stuff, and then we're gonna do something with the concept, and then that's it. Okay, we will continue on next time around. Okay. So let us try to see what if we are going to use the Muller-Breslau with the indeterminate structure, what's going to happen. Okay, now you need to have a pretty good understanding about deflection. So let's consider this kind of beam. You guys okay?
Okay,ค่ะ.
All right. Let's say we have an indeterminate structure. Like this, A, B, and C, okay? If I am going to continue to use the Professor Muller-Breslau principle, if I want RA, the influence line of RA, I will allow the reaction at A to go free, right? But unlike what we had before with this one, when I allow reaction, this one, RA to go free, you only have a roller here. So RA can push this structure up, and the entire structure acts like a door, you know, with a hinge. Goes up straight just like that, because you are left with one reaction. But when it comes down to the indeterminate structure, you know, even if I allow RA to go free, I still have RB and RC. So the structure itself will become something like this. I still have the support here, and I still have the support there, and I have RA pushing it up. So what do you think the deflected shape is going to look like? It becomes essentially the deflected shape of a simple beam, right? This time. So it has, you can guess now, it has to be a curve. It is a curve, yes. So it's just going to go up like this. Okay, no more straight line influence line. So you have a straight line influence line if you have a determinate structure. But once we are dealing with the indeterminate structure, all the influence lines will become a curve. Okay, so let's say RB now. If it is the influence line of the RB, I will maintain my RA and RC, and I will allow RB to go free. What's going to happen? just going to go up like this, right? It is a simple beam being pushed by a point load now. Okay, and RC, you can guess it's going to be somewhat similar to RA, but let's complete the lot. Oops, it's not that straight anyway. Let's draw it again. RC is allowed to move freely, so your beam will be pushed up here like this. Okay, now one more thing that you should always recall is that this is made by applying the unit load on the structure, right? So you can you can be sure that the magnitude of this comes when you apply the unit load at A. So this is 1. This is the magnitude when you apply the unit load at B. So this is 1. And likewise here, this height is also 1. Okay. So now let's come back and take a look at the simple case. So I will use this RB because it's the most common thing to do. Okay. So let's say now you can see in order to get the magnitude of the influence line, we need the deflection. Okay. So let's say if I have a beam. Now, and coming from this case, you know, if I have the unit load at any X location, if you can recall the force method, you would need to calculate the displacement at B. All right. Remember that the influence line is constructed by applying the unit load at, you know, locations along the beam. And if you want to use the force method to calculate this RB after you apply the load at any location at the beam, you need to calculate the displacement at B due to that load at any location, right? So this unit load at any X location is going to push this one down, and we need displacement at B. Okay, which if it is a unit load, we may call this delta B when the load is at X. Okay, when I keep moving the unit load, until it is at B. When the unit load is at B, this can be written as delta at B due to the load at X location, which becomes B. Right? Now it feels familiar. But one more thing, if you are going to construct the influence line by applying the unit load at any X location and calculate delta BX all the time, that is one heck of a problem. And it is a lot of work. So if you can recall, you know, the another theory, we can make our life easier. But before that, let us complete this first. Okay. Now, if I want RB when my unit load is at any X location like this, I want my RB, which is right here. From this, I can write my equation as delta Bx, which is now this displacement here when my unit load is there. But because I have RB, you know, it's gonna become delta BB, which is, you know, the displacement here at the reaction, multiplied by the reaction itself, and this is 0. Okay, so I can solve my RB, and it is going to be equal to minus delta Bx over delta BB. Okay, but like I said previously, if I want to construct the influence line, I need to place the unit load at any X location. So that means I have to come back here and calculate delta Bx and keep changing the load. Yes, if I did not know the Maxwell reciprocal theorem. Okay, now Maxwell reciprocal theorem is something like this. If I have the beam and I put the unit load here at B, again, this beam is going to come down. If I want to calculate the displacement right here at the same location as this unit load, this is called delta at location X due to the load B, right? Now, Maxwell reciprocal theorem says that delta Bx is basically equals delta xb. So that means I can rewrite my equation as RB is equal to minus delta xb divided by delta bb. So do you know what this means? It means that if you want your displacement, or if you want this displacement caused by the load at any X location, instead of placing the load again every time, you can just place the load at this location B and calculate displacement at any X location instead. Meaning, if you know displacement at any location, if you know this, you can make use of this displacement to obtain RB. Generally, when it comes down to this class, I don't have any purpose to test you if you can calculate displacement. So generally, I would give you the formula to calculate displacement, or I may give you the displacement right away. What you need to understand is how to turn the displacement into the force by using this application. Okay, So that shall warm you up to the influence line of the indeterminate structure. Again, I don't have the purpose to test your ability to calculate displacement. So I may either give you this number right away or the formula to calculate this. Okay, I used to give formulas and students don't know what to do, and turns out to be a mess like most of the time. In fact, it is very easy, but I understand that you guys always have the mental block with the influence line. Okay, so that's it. The whole idea is right here. Once you can unlock one redundant, the system becomes the determinate again, and the rest of the function can be solved. But you need to write the equation. Okay, so that's it for today. Is there any question? We should have only one more class, and then this semester shall be over for structural analysis. Time to celebrate, right? It's all quiet. So no question. So I'm gonna stop the share and stop the record. Okay.